civil engineering
Yeah.
with us in Singapore. But her PhD project is geophysical machine learning applications in geophysics. And she's worked on all kinds of field geophysical data. She is now with us here at Purdue as a postdoc. So she will talk about image logs today. Go ahead.
Yeah, thanks for the introduction. Yeah, so today the topic is machine learning based interpretation of micro-resistivity image logs, including inpainting and clustering. So here's the outline. So first I will give the motivations of this project, and I will introduce our work on self-supervised inpainting and unsupervised facial clustering, and I will end this presentation with some conclusions. Yeah, let's start with the introduction part. And yeah, so this is Lumberjay's electrical imaging tool, formation micro-imager. It measures local formation resistivity by pushing these electro pads against the borehole wall. Usually the total width of those electro pads is usually less than the borehole size. This would lead to some unmeasured gaps in the collected data. As shown here, the measured resistivities can be visualized as two types of images. The first one is static image, and the second one is dynamic image. So the vertical axis is the depth, and the horizontal axis is the azimers, ranging from 0 degree to 360 degree. For the color pixels in the static image, they are normalized over the entire log interval, so they can reflect large-scale variations associated with lithological change or the geologic events. For dynamic image, the color pixels are normalized within a sliding window, so it has a higher color contrast. It can show some detailed structural features. So those micro-resistivity image logs, they are actually unrolled high-resolution images of the borehole walls, and they usually contain unmeasured gaps due to the limited width of those electrode pads. And we can also observe many geological features from the images. Like here we can see a group of aligned sinusoidal curves. They are interpreted as low-angle beddings intersecting the web wall. So these image logs are very useful for reservoir characterization, and they are widely used in the analysis of lithofacies, stratigraphy, and the fracture networks. So in this study, we focus on lithofacies analysis from the micro-resistivity image logs. This topic is confronted with many challenges. Like firstly, the image logs are not complete. Moreover, a manual interpretation of the lithofacies remains dominant in oil and gas industry, which requires massive time and workforce and lacks consistency and repeatability. So here comes the machine learning method, which holds great potential to accelerating this lithofacies analysis process. But these methods are hindered by the insufficient label data or even the lack of ground truth. So in this work, we propose a two-stage automatic image log clustering workflow without the use of labels. So the first step is to do self-supervised inpainting to intent the borehole images to get the full images. And the second step is to segment the inpainted images into different clusters with different geological meanings based on unsupervised learning. So in both steps, we don't need to have labels. So let's move on to the first part, self-supervised micro-resistivity image log inpainting. So here, inpainting means to fill the image gaps with coherent structures and textures. So conventionally, we can use compressive sensing or template matching based method based on multi-point statistics. But these methods, they require extensive iterative processing, and they are ineffective for complex formations or for wide gaps. Recently, machine learning methods, mainly convolutional neural networks, have been used in image log inpainting. However, the performance of this method can be further improved. So among various CNNs, UNet is a popular one. It has a U-shaped structure with skip connections. So it can generate higher resolution images compared to a conventional autoencoder without skip connections. And the recent development of attention mechanisms has led to the development of swing transformer, which have surpassed conventional CNNs in many computer vision tasks. So in this work, we just adapt this swing unit for image log inpainting tasks. So swing unit is a hybrid model combining the strengths of the swing transformer and the unit. So here it is the key mechanism for swing transformer, which is named a self-attention mechanism. It is proposed in this renowned paper, Attention is All You Need. So in this paper, given this sentence, attention is all you need, the 5 words are converted to 5 1D vectors through an embedding layer. And these 1D vectors are named word tokens. Then each word token would generate a query vector, a key vector, and a value vector through linear layers. So by calculating the dot product between a query vector and every key vectors, we can get the weights of different value vectors by applying the softmax function to the product. Then the updated token is actually the weighted summation of all the value vectors. So we can repeat this process for all the query vectors, then we can get the same number of updated tokens. So intuitively, the self-attention mechanism learns to derive meaningful outputs by selectively assigning different levels of attention to different parts of the sentence. Then how can we extend this mechanism to 2D images? We can achieve it by just split the images into small patches. Like in this example, the images are split into patches of size 2 by 2 pixels. And in order to improve computation efficiency, the self-attention mechanism is computed within a local window of a fixed size. So in this case, the size of local window is 2 by 2 patches. And moreover, those local windows, like marked with those red brands, are shifted in consecutive layers. So by moving them, we can achieve cross-window connections. So the term swing actually comes from this shifted window-based self-attention mechanism. And here is the, okay, sorry. Yeah, so this is the entire structure of our neural network. It inherits the structure of a unit. So it has a U-shaped symmetric encoder decoder structure with deep connections. The input data have 2 channels corresponding to the static image and the dynamic image. So those image data are converted to 1D tokens through this patch partition and embedding layer. Moreover, the basic encoding blocks in green and the bottleneck block, as well as the basic decoding blocks in blue, they are all constructed with swing transformer blocks. Okay, yeah. So with the swing transformer blocks, we can significantly enhance the feature learning capability of this neural network. Moreover, each encoding block ends with a patch merging layer, which reduces the height and width of the feature map while increasing the channel number. And every decoding block starts with a patch expanding layer, which is an inverse operation of the patch merging layer. So with patch merging and expanding layers, we can change the size, that we can gradually shrink the size of the feature mask through the encoding path, and also gradually expand it through the decoding path. So these two layers enable hierarchical learning for this neural network. Additionally, the skip connections in between retain fine scale details lost in the encoding path. So it helps us to get higher resolution results. And at the output layer, those 1D tokens are converted back to the integer domain through the reverse patch embedding layer. So at this layer, we get the final intended results. And this is our objective function used in training. So we use X to denote the raw dynamic image or the raw image patch. And we create a binary mask for each patch with 0 and 1 assigned to the unknown and the known pixels. We also apply a random masking function G to the raw image and get the direct input to the network. So with this random masking function, we actually create artificial gaps with known branches to assist the training process. And here's the results given by the neural network. So the loss functions, actually the mean squared difference between the raw and intended images in the known pixels. So during training, we just the weights of the neural nets, which is marked with theta, they are optimized by minimizing the reconstruction error in the known pixels. So we apply our method to data from Delaware Basin, and it took us 1.5 hours to train a model on one NVIDIA A100 GPU. And this figure is the learning curves that shows the evolution of the reconstruction error at different epochs. So we can observe that the training loss, validation loss, and test loss all converge to very small values after 60 epochs, demonstrating that the excellent generalizability of our model for data from this region. And let's further examine the inpainting performance of different methods for a patch from the test set. So the upper and the bottom rows are the static images and the dynamic images. And from left to right in each row are the raw images, bilinear interpolation results, unit predictions, and our model predictions. So obviously, the predictions given by our model exhibit continuous structures and textures with minimal artifacts. Contrarily, the bilinear interpolation results contain a lot of interpolation artifacts as indicated by those arrows. And for the unit predictions, they are impacted by the imprints of those missing gaps. So for example, the imprints might not be very obvious, but the imprints are more pronounced. For this example, this is another patch from the test set. So we see a lot of imprints, but in the predictions given by our model, we observe mild imprints. So our model outperforms the bilinear interpolation method and the unit in terms of inpainting. So after we get the complete image with inpainting, we can do unsupervised image log clustering on them to get some meaningful faces. So clustering algorithms is a type of unsupervised learning technique that can automatically separate data into groups of similar objects. So in this work, we use two clustering algorithms. The first one is k-means clustering, which is very popular and simple. It works by minimizing the inter-cluster variance to group the data points into different clusters. And the second type is hierarchical agglomerative clustering. So it works by iteratively merging the two most similar clusters until all data points are assigned to one cluster. So after hierarchical clustering, we can get tree-like structure showing the merging process. So by cutting this tree at different levels, we can get different number of clusters. And here's the detailed description of our clustering workflow. So in this workflow, we only attend to the dynamic image logs, which shows detailed structures and the textures, because we want to get fine scale lethal fishes. So in the first step, we apply k-means clustering to all the pixels of the dynamic image and separate those pixels into 3 classes. So from class 0 to class 2, the color intensity increases. So based on the results, we can get discrete dynamic image where class 0, 1, and 2 pixels are plotted in black, orange, and white. The next step is to compute the content curves of class 0 or class 2. So the content curve is the fraction of the class 0 or class 2 pixels at each step. So based on the content curves, we can compute the absolute gradient curves of the content curves with respect to the depth. And for the third step, we want to find the peaks of the absolute gradient curves. So those peaks are potential lethal fishes boundaries because they indicate abrupt component changes along depths. So as shown in this figure, those peaks are very dense. So we want to subsample them. So we add a thread coding parameter, which is the minimal spacing of neighboring peaks to downsample those peaks. So in this case, this parameter is set at 32 centimeters, meaning that the vertical spacing of the 2 neighboring peaks should be no smaller than 32 centimeters. So with this criterion, we it's not clear. Yeah, so with this criterion, we select a bunch of peaks denoted with the Phi process, and the corresponding boundaries are marked with the Phi lines in the 2 plots. So with those boundaries, we can split the image logs into small patches, and we believe the visual patterns within each patch is uniform and consistent. So the next step is to extract feature vectors for each patch. The feature vector is the means and standard deviations of the content curves and the absolute gradient curves for each patch. And the last step is to apply the hierarchical agglomerative clustering algorithm to the extracted features to get the clusters. So we apply this workflow to the intensive data data, and we get 8 clusters out of it. So this is the section of the intensive data. From left to right are the gamma ray log, static image log, dynamic image log, and the cluster mean results or the cluster log. So from this section, we can identify thick bedded segments. So these thick bedded segments can be further characterized into different bedded clusters. So the first bedded cluster is cluster 1, defined as thin horizontal laminations. And the next cluster is cluster 2, defined as thick dark red layers alternating with thin orange to pale yellow layers. And let's move on. We can see cluster 4, defined as thick pale yellow layers interleaving with orange to dark red layers. So cluster 4 is actually an inverse pattern of cluster 2. And this is a new sample section. We can observe more bedded clusters from them. So the first one is cluster 6, which is perturbed or faint laminations with low color contrast. And the next one is cluster 7, defined as low angle thick laminated layers. So apart from this bedded clusters, we also have unstratified clusters. Like class 0 contains massive dark red blocks. And this cluster 3 which is classic, churned, blotchy with a bright background. Let's move on to cluster 5. it is dominated by thick pale yellow segments, but they don't present clear laminations. So to conclude, we propose a two-stage automatic facial recognition workflow for micro-resistivity image logs. So the first step is self-supervised inpainting using swing UNet. The trained model achieves exceptional inpainting performance for image logs from the Delaware Basin. And this self-supervised training process allows us to easily update the model to other data sets by transfer learning. And the second step is unsupervised image log splitting and clustering. So after this step, we got 8 clusters for the Delaware data, and the 8 clusters exhibit distinct lamination characteristics. And we want to work with geologists to get a deeper understanding of those clusters in the future. Yeah, finally, we want to thank ExxonMobil Technology and Engineering Company for sponsoring this project and providing the data. Thank you.
Questions? I have a question on the same thing. Are you